There's no such thing as an unknown hazardous material incident. You know something about the product. If it's a drum that's been hit by a forklift and it's leaking, you know what? You know it's a liquid, right? Or it's a powder laying on the road. In fact, the first thing you know is physical state, for most part, right? Let's talk physical properties. Physical state, solid, liquid, or a gas. Okay? That's the first thing you know probably about any hazmat incident. First of all, if there wasn't a suspicion that it was a hazardous materials, you wouldn't have been called there to begin with, right? So physical state is probably the first thing you can figure out. So what are the hazards of the physical state? If it's a solid, do we sort of consider that the easy day versus a gas, right? On the extremes, a solid, a liquid, or a gas. For the most part, we typically think of the solid as being the easy day. Now, there are some exceptions to that. Many solids can be energetic materials. They can be explosives. Many solids can be reactive chemicals like oxidizers. Many solids can be radioactive. So there are exceptions to that rule, but generally speaking, keeping the material from moving from one place to another is really what we're trying to do as a hazmat, right? Solids are usually fairly easy to contain. And the other key thing with solids is because of what we found out in the salts, most of all salts are what physical state? Solids. And problems with solids we found typically start when we do what? When we get them wet. So the key thing here is keep them dry. And beware that there may be some very, very hazardous solids that we have to deal with. But the key point is they aren't typically jumping up at us and getting into our breathing space or getting into the air where it can cause harm, unless it is what type of a solid? Anybody ever hear the term sublimating? What's sublimating mean? Goes straight from a solid to a gas without ever becoming a liquid. So we want to know if we got a sublimating solid. So if it's a solid on the ground that people are smelling down the hallway, what's that telling you? It's a sublimating solid. Okay, it's giving off vapors, and there's another way to tell if it's sublimating. Okay, that we'll get to in a second. Next thing, liquid. Well, what's the problem with liquids? All liquids do what? They move, right? They evaporate. All liquids evaporate, and some solids evaporate. And what is the number one determining factor about how fast a liquid will evaporate? Vapor pressure. So the next thing I would really like to know is, what is the vapor pressure? What is the vapor pressure of that material, right? And everybody understands the concept of vapor pressure, right? Definition of the concept of vapor pressure is the pressure exerted by the surface of a liquid and some solids against atmospheric pressure. You got this bucket of methylethyl chicken fat, and you have molecules in this open container, and you have atmospheric pressure of 14.7 pounds or 760 millimeters of mercury pushing down on the top of that liquid. That's one of the things that keeps that liquid in a liquid state. But there's this thing called the kinetic molecular theory. And the kinetic molecular theory says that all molecules are constantly vibrating, unless you get them down to absolute zero, which is negative 463 degrees Fahrenheit. Then they stop moving, theoretically. But all molecules are constantly vibrating. And because they're vibrating, occasionally, those molecules will escape the surface of the liquid. We call that evaporation, right? Now, if I apply more energy to this, in the form of heat, what are those molecules going to do? They're going to vibrate faster, faster, and faster, and more of them are going to escape. This escaping of those molecules off the surface of the liquid is called vapor pressure. It's the amount of force pushed up against the atmospheric pressure by the vibration of those molecules. The closer this pressure gets to 760 millimeters of mercury, the more volatile it becomes, the more evaporation occurs. And once we get this stuff to the temperature at which vapor pressure equals atmospheric pressure, we have reached the boiling point, and it will begin to boil. So boiling point, definition, the temperature at which the vapor pressure of a liquid equals atmospheric pressure. Okay, everybody all right with that? So the next thing I really want to know is, I want to know how fast this is going to become this. Because once it becomes a gas, or a vapor in this case, once it becomes a vapor, then we have a significant exposure hazard. You know, if we think about it, water has a vapor pressure at room temperature, which is always measured typically at 68 degrees Fahrenheit or 20 degrees centigrade, of about 20 millimeters of mercury. How fast does that evaporate? Not real fast. No, I mean, not that you can sit there and watch it. You could if you like. But how about rubbing alcohol, which is what? Rubbing alcohol is isopropyl alcohol. 33 millimeters of mercury. How fast does it evaporate?
Pretty fast.
Pretty fast. How about acetone? Fingernail polish remover. 180 millimeters of mercury, right? Boy, you open up the can of that, you can smell it down the hallway, right? That's giving us an indication that we have a high vapor pressure material. It's a clue that this stuff is becoming airborne. And then we have things going the other way. 1, 2, 3, 4 millimeters of mercury. How fast is that going to evaporate? Not. That's VX nerve agent. I can open up a can of open VX nerve agent and set it in the middle of the room. It ain't going to hurt anybody at 68 degrees Fahrenheit because it's not giving off enough. And I wouldn't want to get down on my hands and knees and smell it. But it doesn't have enough vapor pressure to become airborne quickly. Or malathion, add another 0 to that. Malathion pesticide. You ever get any calls to the house that, man, they sprayed the yard next door with pesticides and it's making me sick. This pesticide's going to make me sick. Is that what's making them sick? No, it's the stenching agent they added to it to tell you to keep your butt off the grass until the stuff goes away. That's what they added to it. Malathion is extremely low vapor pressure. It's a contact hazard. Okay, the third thing I'd like to know is water solubility. Oh, and there's a couple other things that would be nice to know. If it becomes a vapor, or when it becomes a vapor, I'd like to know the vapor density. Is it going to sink or float in air? Bottom line is, if you don't know, assume that it's going to sink. That's probably your worst case scenario. Anybody know how to calculate, if you know the name of a material, how to calculate what the vapor density is? If we take methane, each atom in that molecule has an atomic weight, right? Carbon has 12, and each of the hydrogens have 1, right? We know that on our periodic table. So the total weight of that molecule is 16. Dry air weighs approximately 29. So if the molecule is less than 29, it's going to float, and if the molecule is heavier than 29, it's going to sink. Now there are some.
So if you're in Florida and it's wet air.
Well, temperature and humidity will affect that, but not real significantly.
Does it weigh less or more though?
What, air? What's heavier? Humid?
Yes.
Hot air? No. Cold, humid air or warm, dry air? Cold, humid air. What are the best flying days? Anybody here a pilot? Yeah. Where do you get the best lift on an airplane? Cold air, because the air is thicker and heavier and you get more lift out of it. Anyway, so just compare the molecular weight. Compare the molecular weight to 29. Just compare the molecular weight to 29, and that'll tell you whether it's going to sink or float. And the vast majority of vapors generated from a liquid are going to be heavier than air. In fact, I will take the statement and say all vapors generated from a liquid at room temperature will be heavier than air. Because once you hit 3 carbons, once you hit a 3-carbon chain, let's hear 12, 24, 36, 37, 38, 39, 40, 41, 42, 43, 44, you're almost twice, you're about 30% heavier or 50% heavier than air once you hit a 3-carbon chain. So there's not a lot of compounds out there that are real small compounds. You know with that? Solubility tells me a lot about respiratory disposition, where it's going to land in the respiratory tract, whether or not it's water soluble. It's going to tell me decontamination. If I got something that's highly water soluble or significantly water soluble, water's decontamination solution of choice. If it's not water soluble, we got to add something to the water to help get it off. That's it. Those are the physical properties I'd like to know. When I start seeing vapor pressures, now this is the world according to Doug. This is not based on any scientific fact. It comes from 29 years of experience in hazardous materials. When I start seeing vapor pressures greater than 100 millimeters of mercury, you have my full and immediate attention. Because that's telling me that stuff is going to become airborne very quickly. Especially you put that 100 millimeter of mercury vapor pressure liquid on the floor inside an enclosed building, now you really got my attention. Now that's not to say that things with lower vapor pressures can't be really hazardous to us, because if we look at toxicity, which is where we're going, if you could only figure out 1 or 2 things about the toxicity of a material, what would you like to know in order to analyze the risk to your personnel and the public? IDLH. And one other. Route of exposure. Speak up, don't be afraid. Those are the 2 things I'd really like to know about a material to determine hazards. How does it get into the body and how toxic is it? Well, if I got something with a vapor pressure of 20 millimeters of mercury, which is below 100, but its IDLH is 2 parts per million, then that 100 vapor pressure really doesn't mean anything, because I got something that's extremely toxic, right? So you got to take vapor pressure in comparison to IDLH.